Hey, good afternoon, everyone.
Good afternoon.
Hope you all had a good weekend, and I hope that everything went okay with the day that we weren't here. I asked you all to watch that video on the mean value theorem. I'm going to talk a little bit about it today. And I thought I'd start with a question. I want you to just read through this. I have a question that I'm going to ask for you to answer, but I'm going to do a poll, okay? So read through it, and I'll answer any questions that you might have about the question here. But let me put the poll up first. Let me see what poll I have here. 2 questions. No. Yeah, there we go. So on this poll that I just launched, it doesn't say what choice 1 and choice 2 are, but choice 1 would be yes, and choice 2 would be no. Okay, so you don't have to answer right now if you have a question about what I'm asking. And this is not a grade or anything, so don't freak out, okay? Are there any questions about this situation that I'm trying to describe here? While you're thinking and answering, there's 2 cars lined up. They're going to start the race. They're going to race down the track, and at the very end, the end of the race, they're going to cross the finish line at the exact same time.
Sorry, my audio, I'm on my phone.
Yeah.
Could you read the question?
Yeah, it says 2 cars line up for a race. The light turns green and they both speed down the track. Both cars finish, they cross the finish line at the exact same time, so they tie at the end. And my question is, do you think that there was a point in time during the race where both cars were going the exact same speed? So there are any other questions?
Is the question if they were going the exact same speed at the same time at some point in the race?
At the exact same point in time. Yeah, so I'm asking, is there a point in time? You can think of it this way. Both cars are driving on the track, right? You can imagine that you can look down at your speedometer, right? So the question is, was there some point during the race at the exact same point in time where both drivers would look down and see the same speed on their speedometer? But it has to be the same speed and it has to be at the exact same time. Interesting results here. I'll give you another 10 seconds. What's that?
Oh, what are the? Is it yes or no?
It's yes or no. Choice 1 is yes, you do think that there's, and choice 2 is no. All right, that's almost everyone. Let's take a look at these results. So 14 out of 16 think yes, there is a point in time that both cars are traveling the same speed, right, at the exact same time. And 2 people say no. I don't think I've ever had that response from a class before. So now you have to tell me why. So I want someone to justify it. So many of you think that there is a point in time. Convince me. Or did you just say yes because I wouldn't be asking unless the answer was that yes?
No, that's not it at all. It makes sense reasonably if they're both okay. If at the very least, if they cross the finish line at the same time, that means that whatever their average speed ended up coming out to be the same, which means that at some point their speeds would have probably crossed. It lines up with what I remember we talked about last time. it also makes logical sense. I can't go much deeper than that though.
No, that's pretty good. Now, the thing is, we need to make sure we understand, I'm saying that the point in time, okay, is during the race, not at the beginning, because of course at
Yes.
the beginning, they're both
Of
at
course.
0, okay? And at the end, they come across the line at the same time,
They
right?
aren't necessarily going the same speed at the end
They
either.
won't necessarily be going the same speed, but I'm saying not at those two endpoints. Somewhere in the
Yes.
middle, are we guaranteed that we have that? So, all right, I like Hunter's kind of rationale for it. Anyone want to expand on that, or anyone who wants to say choice 2, no? Want to explain why it's not guaranteed?
So I said no, because like Hunter said, they're going the same average speed, which means that they have to be going the same speed at some point during the race, but not necessarily at the same time.
I like that argument too. So let me draw a graph to try and persuade the 14 of you who said yes. Let me try and draw a graph to kind of illustrate what we have going on here. All right. So let's say that this is time, and let's say this is distance. All right. And I'm going to draw basically 2 cars. So the first car we'll say is the blue car. Okay. At time 0, this car has gone nowhere, right? So we can look at that as a 0.00. And then at the end of the race, at some point in time, who cares where it is? Who cares how long it took them? At some point at the end of the race, let's say this is the end of the race, they had gone a certain distance, which would be the length of the track, right? So this would be the finish line distance, whether it be, you know, a mile or whatever it is. So the way that that car gets to this point can be, you know, it depends on how they drove, right? They could have drove slow in the beginning and sped up and slowed down, who knows, right? But I want you to consider this picture. They could have gone very slow, and then at the end they could have sped up and they could have got there, right? And then the other car, let's say the red car, could have done a little differently. It could have gone very fast in the beginning and then slowed down at the end and got there, right? That could have happened. Now, what Maddie's saying is that, yes, they both have the same average speed because they both cover the same distance in the same amount of time. Meaning, if you look at the line connecting these 2 points, the slope of this line would be the distance over the time, right? How far they went over how long it took them. This would also be their average speed. And that would be the same for both cars, right? So that's what Maddie was saying. Both cars both have the same average speed. And the mean value theorem says that they both, if you have an average speed at some point in the trip, you had to go that average speed, which means there has to be somewhere on this red curve, there has to be a tangent line that's parallel to the green one, right? And somewhere on the blue curve, there has to be a tangent line that's parallel to the green one. Do y'all agree with that? Individually, the red and the blue both have to have tangent lines that are parallel to the green, but does it have to be at the same point? Right, that's what I was asking. Is it happening at the same point? So like I can look at this first one. Come on, where's my cursor?
As soon as you drew the graph up there and I started looking at it, I immediately saw what you were going to do and was like, well, yep, nope, there it is. You just
right. So what I'm trying to do is convince 14 of you that it's not a simple problem. This is complicated. There's some complexity to this that you have to take into account, right? So from that picture, have I visually tried to convince you that yes, they both have the same average speed, and that at some point in time they both have to achieve that average speed in their trip? But it looks like it doesn't necessarily have to be the same point in time. Do y'all kind of see that from the picture?
Yep.
Okay, now the answer is yes. All right, it is yes.
What?
Yeah, I know. Okay, so here's the reason why I like to show this example is because this this is one of these things where in the real world, we run into these things quite a bit in the real world, where you have something that you're looking at and you have people have different intuitions about what it may be, right? You're like, oh, I think it's this, but they can't quite explain why. It's just to them, it makes sense. And then you have other people who are like, no, I look at it this way, and that makes sense to me this way. And they go back and forth and they argue their point, but there's no real way to settle it, right? And that's what mathematics is there for. It's to settle something like this so that we no longer have any sort of, there's no debating, right? Someone's going to be right here and someone's going to be wrong, but the math is going to be what's going to prove it. All right. So
Wait.
I'm now prove this to you. All right. I'm going to prove to you that there is a point in time for both cars that they both must be going the same speed. All right. And the way I'm going to prove it to you is not something that I would ever expect a student to come up with on their own. This is a good glimpse into the way mathematicians solve problems like this. Right. So you're more along, think of it as you're more along, going along for the ride here. All right. I wouldn't expect this to come out of your own minds at this point. All right. Now, if you become a math major, this is something that you have to start to develop. All right. Okay. So here we go. So this is what I'm going to do. I'm going to first state what I'm going to try and show you. All right. So let me start labeling some things. Let's let this be the red car. The red graph, I'm going to call that R of t. It's a graph, right? R of t is the graph of the path of the red car. And then the other one, I'm going to call that B of t, and that'll be the blue car's path, right? Now, do you all agree with me that these are continuous functions? Think about a car that has to go from a stop and speed up and then cross a line. It doesn't like disappear into another dimension and show up on the track in a different location, right? Everything is continuous. The speed gradually will increase and decrease. You don't go from 20 miles an hour to 50 miles an hour and skip everything in between, right? These should be nice continuous functions. Agreed? Okay. So now that I've defined this, here's what I want to show you. I want to show there exists a point C in the interval. Now I need to label this because I need to label my x-axis or my t-axis. Let's agree that this is 0, and then let's just let the end of this be, I'm just going to come up with some arbitrary thing. I'm going to call this, let me call it little b, all right? So my interval is going to be between 0 and b. I want to show you that there's some value, some point C in here, okay? I don't know where it is yet, but somewhere in here, I want to show you that when at that point, what's true? They both have the same speeds, right? Which means that the derivative of the R function at t must be equal to the derivative of the blue function at t, which means they would have the same slopes of their parallel, their tangent lines would be parallel at that point. Sorry, forgot to put C in there. C. All right, any questions on what I'm trying to show you? Any problems with, would I convince you, would you be convinced if I could show that that's true? Okay, would you? Because I need to make sure you're okay with this idea that I'm going to try and come up with some value C that lives inside that interval that the derivatives would be equal there. And if I show you that, then I have convinced you that both cars must travel the same speed at some point in time. Yes?
Yeah, I'll be convinced.
Yes, everyone okay with that? Okay, so now I'm going to go try and do it. All right, so this is what I want to do. Let me go try and do it. So here's how I'm doing it. It's going to be tricky. What I'm going to do is I'm going to define a new function. Okay, a new function, and I'm going to call it capital D of t. Let capital D of t be the difference between the two functions. It's f of t minus b of, oh, sorry, not f of t, r of t minus b of t. So what I'm doing is I'm asking you to consider a new function that just calculates the difference between how far each car has gone. All right, this new function. So think about this new function and what it must look like. What would the value of this function d be at 0? So how far apart are the cars at 0? If I plug 0 in here, isn't it the difference between the cars right here at this point?
It's to be 0.
It would be 0, right? So if I were to graph this new function d, at 0, it would be 0. And what would it be at b? What would the difference between how far apart the cars are at b at the end?
Also 0.
Also 0 because they tied, didn't they?
Yeah.
Okay, so I would have a graph like this. Now, capital D is continuous also. The reason I know it's continuous is because I'm taking the difference between two continuous functions. So if you take the difference between two continuous functions, you still have a continuous function, which means that when I draw the curve D, it's got to connect this point to this point, but I have to draw it without picking up my pencil, right? What it does in the middle really doesn't matter. It just has to connect. So if I connect those, doesn't matter what happens. What do I have now? What theorem do I have? No.
Is this Rolle's theorem?
That's Rolle's theorem, okay? Which is where the mean value theorem comes from. But this is Rolle's theorem. We have a function, d, that has the same values at both endpoints. And so by Rolle's theorem, what can I say? By Rolle's, let me do it this way. Since capital R of 0 equals capital B of 0, and capital R of B equals capital B of B, right? So when I look at the two endpoints, they give me the same values. There exists a C in the interval 0b such that what's true? So what can you tell me about capital? This is capital D graph right here. What can you tell me? If this and this are connected, right? There's a straight line connecting those. The slope of that line is 0, isn't it? The slope of this line is 0. Somewhere
Yes.
in here, I'm guaranteed to see where the slope of the tangent line of D would be parallel to this, right? So Rolle's theorem
Yes.
says there exists a C somewhere in 0b such that the derivative of D at that C is 0. Now, what is the derivative of D? If I ask you to take derivative of this, take the derivative of the left side, you get D prime of T, right? Take derivative of the right side, we have subtraction. You do them separately, don't you? Take derivative of each one. So isn't the left side of this actually just R prime of C minus B prime of C equals 0? Okay, add B prime of C to both sides. Just move this over to the other side. And what are we saying? R prime of C equals B prime of C, which is exactly what you told me I needed to show you. Right?
Oh man, that's crazy.
Yeah. Right. You said you would be convinced if I could show you that R prime, that there was some point C where R prime of C was equal to B prime of C. So I created a new function, capital D, which was their difference. Use the fact that at the endpoints we have the same values. Rolle's theorem says, oh, then if there's a flat line between the two, somewhere in there, we've got to have our function have a flat derivative or a derivative of 0. So I said, okay, well, somewhere in there, the derivative of D is 0. But the derivative of D is just the derivative of each of these subtracted, add it to the other side, and I've shown it. So interesting, right? Interesting.
So where would that be on your example graph? Like, would that be during their acceleration and deceleration? They would just cross at some point?
Well, I drew
Like,
this
obviously.
in a way. I drew this in a way that there's, see, this theorem, this idea, we're guaranteed at least 1 point. At least
Yeah.
one. Okay. At least one. There could be more than one, right?
Yeah.
In my picture, I don't know. It's somewhere, it's probably somewhere. I don't know. I mean, it's here. It's guaranteed to be here.
Yeah.
Not sure exactly where, but it's here.
Yeah. It would be while one of them's accelerating, the other one's decelerating. They just cross at some point effectively.
It's probably somewhere in here. From the picture I drew, it's probably somewhere in here.
Yeah.
But I know it's there. I know it exists.
Yes.
I know it exists. So it's really an illustration. I don't want to eat too much more time out of class because this isn't something that you're going to be tested on or anything. It's really just to show you a glimpse again into the way that you have to analyze things when, yeah, really this is the way computer science and math people have to think. They have to find a way to use only what they're given to show something, right? All right, we're going to move on. So today we are going to cover the next section. Now, I know you may have some questions about maximum and minimum values, okay, and how we find the max and min on closed intervals. But I do want to make sure that everyone understands that the method we used in 4.1 to find the absolute max and min of a function on a closed interval, we call that the closed interval method. I want to make sure everyone understands that you have a procedure for that, okay? If you're ever trying to do that, find the max and min on a closed interval, you have the procedure. You find the critical numbers, you take those critical numbers, you plug those critical numbers into the original function, you plug the endpoints into the original function, and you compare them, okay? That's the method. Now, within your homework, if you came across functions where you're like, shit, I don't know how to solve that, like, I don't know how to set that equal to 0, I don't know where that exists, that's a different issue. That's an issue we have to practice more with. In 4.3, we will have more time to practice that. The most important thing for 4.1 is, do you understand the method for the closed interval? All right. So
I'm spacing. What were the critical numbers again? I'm spacing on that.
I forgot too. Can someone tell me? What are the critical numbers of a function?
The critical numbers of a function are when the derivative, right? Derivative equals 0 or it's undefined or something.
That's right. So the critical numbers of a function are any numbers. First of all, those numbers have to be in the domain of the original function. Okay, we have to be talking about numbers that are allowed to be plugged into the function to begin with. Any number that can be plugged in the function that makes the derivative 0 or the derivative not exist are called the critical numbers of a function. Anywhere where the derivative is 0 or the derivative doesn't exist. And this is in 4.1. If you look down, I defined it here. Critical numbers definition right here. A critical number of a function is a number C in the domain of the original function. So that's what I was saying. You have to be able to plug it into the original function such that either the derivative is 0 there or the derivative doesn't exist there. That's a critical number. Close. Okay, so now we're going to get on to 4.3, derivatives in the shapes of graphs. Let me make this a little bigger for you. All right, so the derivative, one of the most important aspects of a derivative of a function is that it helps us determine where a function is going up and where it's going down. Because remember, the derivative is the slope of the tangent line, right? So if the slopes of your tangent lines are positive, that should give you some indication that the graph is increasing, going up. And if it's negative, that should tell you that the graph is trying to go down. Here's an illustration. So if the derivative of a function is positive, greater than 0, on some interval, then the function, the original function, must be going up there. If the derivative is positive, the original function goes up. Okay, if the derivative is negative, the original function goes down. And if the derivative is 0, then we have to be flat. And this illustrates this. Okay, here's an example of a function in blue, where if I were to look at this and move across this function, notice that the slope of the tangent line is always positive, right? No matter where I am on this graph. So anywhere on this graph, the derivative is positive, and so the graph should increase. So if you look at it from left to right, because we always read graphs from left to right when we're talking about increasing, when you go from left to right, we're going up, right? Now, if the derivative is negative, then we should expect to be going down, right? Always negative slopes on those. And if the derivative is 0 all the time, then we should expect to see a constant function. So derivatives are very useful in determining where something goes up or down, all right? I know a lot of you are going to have to take Cal 2, right? Here's my notes for Cal 2. Oops, wrong one. Here we go. So in Cal 2, deep into chapter 8, there's a part of this where we're trying to look at something called a series. Don't worry about it. But in one step that we have to do, we have to show that a function is decreasing. And the way that we show, how do we show that a function is decreasing? We do this. We show that the derivative of it is negative. That's exactly what I'm telling you right now. That if the derivative of a function is negative, the function has to be going down. If derivative is positive, it has to be going up, all right? So this will come into play later for sure. It's one of the bigger ideas in this class. So we'll get back to this. Any questions on this visually?
When is it when it crosses again? I'm just trying to remember off the top of my head.
Crosses? What do you mean crosses? When what crosses?
I'm trying to remember from like earlier chapters. Isn't it like the derivative or the original function, something crosses it? Yeah, I'm sorry, I'm drawing a blank.
So I'm not sure if you're thinking about the graph of the derivative. If you're talking about the graph of the derivative, anywhere the graph of the derivative crosses the x-axis, that's where the original function should have a slope of the tangent line being 0. That might be what you're
That's what it is, yeah.
Okay. Yeah. So here we're not looking at the graph of the derivative. We're just saying, hey, look, look at the derivative. Tell me when it's positive. If you can tell me when it's positive, then I can tell you when the function's going up. Look at the derivative. Tell me when it's negative. If you can tell me when it's negative, then I can tell you where the function's going down. Make sense? Here's an example of a function that does a bit of both, right? If you start moving from left to right, notice that as we start to move, right, the function's increasing, so we should expect our derivative to be positive. We get to the top, the derivative up there will be 0. Once we get past that point, it's going to go negative derivative. Then we get down at the bottom here, 0 again for the derivative. And then when we go back up, it's going to be positive. So do you see what's happening here? We're changing, right? The derivative goes from positive to negative to positive. Again, positive, negative, right? So think about that. It's up and down, right? Up then down. That's a maximum, right? That's a local maximum up there because our function went up and then had to come back down. So we should have like a peak, a top of a hill. And if our function goes and the derivative goes from negative to positive, right? Then we should be at a lower point on the graph. So do you see how we're going to start to use this to try and identify the peaks and valleys of a function? We're going to be trying to say like, hey, when does the derivative go from positive to negative? Maybe that's where I have a hilltop. Where does the derivative go from negative to positive? Maybe that's where I have a bottom point, a valley, right? So that is exactly what the first derivative test is. Okay, this is what's called the first derivative test. And here's how it goes. it says, suppose C is a critical number of a continuous function. Okay, so when we started this, after we talked about the cars, we said, what's a critical number? Okay, so we all know critical numbers anywhere where the derivative is 0 or undefined. Okay, anywhere that happens, that's a critical number. So let's say that we have a critical number. And, typo, let's say that the derivative of the function changes from a positive to a negative at that number. Then here's what I can tell you. You're looking at a local maximum. So you've got some critical number where something interesting is happening, and then the derivative goes from positive to negative. That means you have to be at a local maximum. If it goes and changes from negative to positive at that point, then you have a local minimum. If it doesn't change, then you don't have a local max or a local min. So I'm going to show you illustrations of this. Here we go again. I'm going to move this slider around. Watch what happens to the derivative. All right, the derivative is either green or red, right? Green is positive, red is negative. So watch as I move. Positive derivative, right? Positive, right, up. Oh, went too far. Yeah, positive to negative, right? Positive to negative. We should have a local max there. We do, right? What happens here? Negative to, oh, stays negative. What's the slope of the tangent line right there?
0.
0. So that's a critical number, isn't it? That's a critical number because that's somewhere where the derivative is 0. But see, to the left of it, your derivative was negative. To the right of it, your derivative stays negative. It didn't change signs. That's not a local max or a local minimum because you didn't have a change in sign of the derivative. On the first one we did, right? At the very top of this, I can't quite get it to get to the top. Let me see. I don't know if I'm gonna be able to, but what's the, don't we have a critical number at the top? Slope of the tangent line up here at the top, that should be 0. So that's a critical number. And to the left of it, my derivative is positive. To the right, it's negative. We have a change in sign. We should expect to see a local max there. And then we have another one over here. Here we have a critical number down here because the slope is 0, right? And so we go from negative and then we switch to positive. Anytime we go from negative to positive, we should expect a local minimum. Does this make sense visually?
Yeah.
The visual part of it's the easy part, I think. The doing it by hand is the hard part, as you're going to see. All right. So there's an example. Here's another one. Oh, wait, hold on. There's a maximum. No maximum. There's your minimum, right? I kind of illustrated again. At this maximum, to the left, we've got positive derivative, to the right, negative. Here, we don't have a max or min because it doesn't change signs. It stays negative on both sides. And then here, we go from negative to positive. So, all right, good. Example time. So for this problem, what the instructions right now are just to do parts A and B of this. All right, we'll do the part C in a minute. So I want us to look at these functions. I have a bunch of them. Okay, we're gonna try and do as many of these as we can. I have all these functions. What we're gonna do is we're gonna find the intervals where the function is increasing and decreasing. I want you to tell me, when does this function go up? When does it go down? And then I want you to use that to determine where we have any local maximums or minimums. Please note, the function I'm giving you right now, I'm not asking you for the absolute max or min. I'm not. I'm asking you for local max and mins. And the reason I'm not asking for absolute max and min is because it's not a closed interval. Okay, if we have a closed interval, then we can find absolute max and mins. But if it's not a closed interval like this, then we can't. Okay, so I want locals. Now, visually, the graph we're about to do, let me go put it on a different page. We're gonna try and figure out where this function goes up or down. But you know what? Let's not look at the graph yet. Let's actually just do it. Let's see what we can do on our own without a graph, and then we'll go to the graph. All right, so here we go. I want to know where this function is going up and down, and I want to know any local maxes or mins, right? So the very first thing I'm going to do is take the derivative. All right, that's the very first thing I'm going to do because I'm going to need the derivative. So let's go ahead and take it. The derivative of this function should be easy. 12x squared plus 6x minus 6. Right? Now, I need the critical numbers. Sometimes, okay, we can call these critical numbers, or we can call them critical points. Numbers or points. You'll hear me say both. Okay, critical numbers or points. And I might even abbreviate these from now on as CP for critical points. So I need to know when this derivative is 0, and I need to know when if it's ever undefined, or if it doesn't exist. All right. That's what I need to figure out. Before I get too far ahead of myself, I want to ask you real quick about the original function. What is the domain of this? Are there any numbers you cannot plug in?
All real numbers.
All real numbers.
Yeah,
You
should be all real.
basically can do anything you want, right? You can plug any number into that, which means, what this means is that if I get any critical numbers here, I don't have to worry about whether or not they actually can be plugged into the original function. I know they can, because the original function can handle any numbers. So let's do the critical numbers. So the first thing I'm going to do for the critical numbers, I need to do two things. I need to figure out when is this derivative 0, and then I need to figure out when does the derivative not exist. DNE does not exist. I'm going to look at these separately. So the first one, when is the derivative 0? Well, that's just a quadratic, right? I set it equal to 0. Let me just divide through by 6. Right, I just divided through by 6. And can that factor? Please tell me this factors. 2x, x.
It does.
1 minus 1. Yeah, it does factor. If it didn't factor, you'd have to use quadratic formula, right? Okay. But luckily for us, it factored. So x is a half and x is -1. So far, I have 2 critical numbers. And again, the thing I don't have to worry about, normally what I would have to do here is check, do these numbers, can I plug them into the original function? I'd have to check that. But I don't, because the domain of the original function is everything. So I'm not really concerned about that for this problem. But I will on future problems have to check, make sure, can I plug those numbers in? All right, now what about the derivative not existing? So take a look at that derivative again. Here it is. I'm not setting it equal to 0. I'm just looking at it. I'm looking at this and I'm saying, are there any problems with that function? Is there anything I can't plug in? No, I can plug anything I want, right? So this will never happen. The derivative will always exist because I don't have anything that makes it undefined. So I have no critical numbers from that aspect. You with me? All right, so this means I know something interesting is happening at -1 and at 1/2, right? Something interesting is happening with this function. Something's changing there. So here's what you do next, all right? And I will just kind of take a quick time out here. This is where I part ways with the way the book does it. And I still haven't found any book that kind of approaches it the way I approach this. So if you go to a tutor or you open your book, it's going to look different to you what I'm about to do, all right? But I just want to say that because if you go to a tutor or something, they're like, what the hell are you doing, right? It's the same thing, just looks different, and so people freak out when they see it. You won't know because it's all, I'm going to show it to you, this is all you've ever seen, right? Okay, so I think it'll make sense though. So here's what we're going to do. We're going to do a number line. We're going to draw a number line. And I'm going to plot these 2 points, -1 and 1/2, all right? I know something is interesting is happening here. So I'm going to break up, that will break up my number line into 3 regions, right? And what I'd like to know is to the left of -1 over here, I'd like to know what the derivative is doing over there. I want to know if the derivative is positive over there or if it's negative. Understand? If it's positive, that will tell me my original function is going up over there. If it's negative, I'll know my original function is going down. So I need to pick a test point. So I'm going to pick any point I want to the left of -1. And it's totally up to me. It's totally up to you. I'm going to pick -2. I'm going to circle it because I don't want you to confuse it with this number. This is a critical number. This is a test point. I've got to do that in all three regions. So I'm going to pick a nice number in here like 0. And a nice number over here, I'll pick 1. 1's a nice one. And what I'm going to do with these points, because I'm interested in what the derivative's doing, right? I'm going to take these points and plug them into
The derivative.
the derivative, because I want to know, is the derivative positive or negative, right? So I'm going to plug them in. So now I'm going to take these points and plug them into the derivative. And all I care about is whether or not I get a positive or negative number. That's all I care about. So remember, your derivative's up here, right? Here it is. I'm going to grab it. I'm going to throw it right over here so we can reference it. There's my derivative. Let's plug -2 in. Okay, -2 squared is 4. 4 times 12, that's 48. Plus, let's see, 6 times -2, that's -12. And then I have -6 again. I think that's still positive, isn't it? It's a positive number there?
Yeah, it'll be
Okay.
like 30, I think.
Yeah, and I really don't even care what it is. I just care that it's positive, all right? Greater than 0, all right? So look what we're saying. The derivative at this point is greater than 0, which means to the left of -1, watch what I'm going to write here. To the left -1, I know that the derivative is positive, right? That's what it's saying. That's what we're saying. What does that tell me about the original function over here? What is it doing?
Increasing.
Increasing.
Going up. So the way I'm going to reference, or the way I'm going to label that, is I'm going to put a little arrow like that to let you know the function's going up right there. Okay. Now we do the same thing for 0. We plug in 0. 0 is going to be easy to plug in, right? You just get -6. 0 to that derivative kills off the first two terms. Well, that is a negative number, right? That's less than 0. So that means everywhere between here and here, my derivative is negative, less than 0, which tells me what about the original function?
It's going down.
It's going down. So I'm going to draw a little arrow like that. And then I plug in 1 and figure out what happens there. So if I plug 1 in, I should get 12 plus 6 minus 6. This is a positive number, greater than 0. My derivative over here is greater than 0, which means my original function is going up. Yeah?
Yeah.
So let's answer the first part of the question, which is find the intervals on which the f is increasing or decreasing. All right, so we can tell from this picture right here what's happening. F is increasing where? So when we talk about where it's increasing, we're talking about the x values. So do y'all agree that to the left of -1 forever and to the right of 1/2, that's where my function's going up, right? So the way I'm going to write that is this: -infinity to -1 union 1/2 to infinity. So remember, these are x values. It's kind of like a domain. You're telling me the x values where the function is going up. So everything to the left of -1, that's this. Everything to the right of 1/2, that's this. Union them together, that's where it's going up.
Real fast, is that a
Yeah.
colon you're using?
I just used the colon.
Okay.
Now f is decreasing where?
-1 to 1/2.
Yeah, right here, in between here, right? Between there. So I'm going to go from, it's decreasing between -1 to 1/2. Now, when we were talking about continuity in the, wait, was it continuity? We talked about increasing or decreasing before. You can close these intervals off. You could put a bracket on the -1 or a bracket on the 1/2. You know what? We didn't talk about this. I take that back. When it comes to increasing and decreasing, you do not need to include the endpoint. All right. You can, it won't be wrong if you do, but you don't have to, because in order to talk about increasing and decreasing a function, you need two points. because you have to compare, is it going up from one point to the next or not, or down? You cannot tell me about increasing or decreasing at a specific point. So I always just put open intervals just to be safe. All right. That's it. We've answered part A. This is part A. I've told you where the graph is going up or down, right? Questions?
Are you gonna ever show us the book method or whatever method you said it differs?
No. There's what they do is this. They use what's called a sign chart. You'll see. I mean, like, you won't see actually. Look, it's confusing what they do. Trust me, it's confusing. All right. Does this make sense to you? Ethan?
Yeah, no, it's good. I had a
Yeah.
college algebra professor who did like almost the exact same things, but without derivative. It was for, I guess, original graph or whatever, but
Yeah. So did they use like plus minus, and like,
it was the same thing with the number line and the positive
Yeah.
increasing, decreasing. Yeah.
okay.
I was just
yeah,
curious.
So if this makes sense, let's stick with this. If I open the book, I can show you how they do it later, but trust me, I mean, when I was learning it, I was like, what the hell are they doing? And then I finally understood what they were doing. Like, why do it that way? Like, it's hard to interpret from a student's perspective what they're doing, because they just use like pluses and minuses. Like they just put here, they put like plus, minus, plus, and then somehow you're supposed to now understand that plus means the derivative is positive, and that means its function is going up. Why not just state what it is? The derivative is positive. Just state it. You'll see this all come together later. It'll hopefully make more sense. Or, yeah, I don't even know what I'm saying anymore because I don't want to show you the other way because it's just going to confuse you. All right, the next thing, part B, find the local maxes and mins. All right, find the local maxes and mins. So we have the first derivative test. The first derivative test says that if we are looking at the critical numbers, right? Now we have found our critical numbers, right? -1 and 1/2, we found them. It says here, if we're looking there, if we ever see a change from a positive to negative, if the derivative, right, ever changes from positive to negative, we're looking at a local max. If the derivative ever goes from negative to positive, we're looking at a local min. So let's go back and look. What did we have?
Changing from positive to negative at -1 and negative to positive at 1/2.
Yeah, it goes from positive to negative, right? The derivative. See, I'm looking at here the red part, not the blue part. The derivative goes from positive to negative. So I should expect a max there, right? What I like about this method is you can kind of see it. Look, you got to go up and down, right? You got to go up and down. I mean, that's why I drew the blue, right? You go up, then you go down. That's a maximum. We have a local max there. And then over here, you go down and up, right? So it's got to go down and up. So that's got to be a local min. Yes? So I'm now going to tell you that for part B, I have a local max. And where does it occur?
-1.
At -1, right? So what I'm going to do is I'm going to plug -1, now this is critical, into the original function. Because I actually want to know the point on the original function's graph where I have that, like, what is the maximum value? I know that it happens at -1, but I need to know the actual value of the function there, the original function. So I'm going to plug -1 into the original function, which was way up here. I'll copy it and paste it. See, I don't need the derivative anymore. The derivative helped me figure out where things go up and down. Now I'm trying to actually figure out how high the original function went, how low it went. So I'm plugging -1 in here. If you plug -1 in here, you should get -4 plus 3 plus 6 plus 1, which I actually want this value. So 6. 6. So the local maximum value is 6. And then the local min, I have a local min, right? And that happens at 1/2. When I plug 1/2 into this function, I should be at a bottom point. So I'm going to plug in 1/2 into this function. And yeah, you got to plumb 1/2 in there. It's going to suck. Okay. So now I'm gonna pause. I'm gonna go look at the graph because I'm gonna have the computer give us this. All right. So here's the graph of the function. Okay. Here's the graph of the function. And technology has come so far. It has come so far because, you know, when I was a student learning Cal 1, I couldn't just go to a website, type in a function and it graph it. And not only graph it, do you see the points it's put up here for you? Like it already has labeled the local maximum. If I just hover over that, it tells me exactly what it is, right? -1,6. Is now we said we should have a local maximum there, right? And then we go down, let's see, what it labeled the y-intercept. That's not important to us right now, but it labeled the y-intercept. It labeled the x-intercepts. It's already done all that for me. And then the local minimum is, look at the x-coordinate, 0.5, that's 1/2, right? And the y value, -0.75. So if I go back to this, this should be -0.75. Keep in mind, these are local maximums and minimums, not global, right? Not global, local.
Well, looking at the graph, it looks like it goes to infinity on both sides, so can't
Yeah.
have a global.
That's right. This would go up and down forever because it is a polynomial function. And so polynomials, if you look at the end behavior of a polynomial, it either does like this or like that or like that or like that. There's only 4 possibilities. So there is no global max, there is no global minimum, but there are local maximums and minimums. So check this out, all right? What we've done here is actually pretty monumental if you think about it, because when you were in college algebra, the things that you did in college algebra were things like, oh, let's go, right? In college algebra, you would have been given this function and you would have been told to graph it. That's polynomial. And in college algebra, you're asked to graph that. And what you do is you'd find the x-intercepts, you would find the end behavior using the leading coefficient test. You would know that the left side goes down, the right side goes up. And then you'd use this thing called multiplicity to try and determine whether or not you actually crossed through or bounced off these x-intercepts. And then you draw a graph. If you don't know what I'm talking about, you know, college algebra was a long time ago. But you would draw it, and one thing you would do here is you would connect these together. And I hope your college algebra teacher told you how high up you go here with these is up to you. Like, we don't know that. Like, we could try and plot more points to get a more accurate graph, but finding out how high something went or how low something went was beyond our grasp in college algebra. We couldn't do it, right? So we just kind of waved our hands at it. We now know how to do this. We can actually graph this now with much more detail because we can find these local maximums and minimums. So we can tell you how high it went, how low it went, right? So it's a pretty big deal.
That's really cool, actually.
Yeah, but we need the derivative, right? What do we need to do? We need to take derivative. We need to set it to 0. We need to figure out where it's undefined, get those critical numbers, right? Let's just run through it mentally again. How do we do this? Take the function, take the derivative, find the critical numbers, figure out what derivative is 0, where it's undefined. Once we have the critical numbers, we draw a number line, break our number line into regions, pick test points. Those test points get plugged into the derivative. We look for positive or negative. That tells us up, down, up, down. Once we figure out up, down, we write down the intervals, and then we go find the local max and mins. We're looking for where it goes up then down for max, down then up for mins. Is that like a 30-second summary of everything right there? Yeah.
Like Turbo Man.
Yep.
Yeah. All right. So that's the idea. All right. Theoretically, there's nothing else. What gets hard now are the functions. This was a polynomial, right? Was it hard to take derivative? No. Was it hard to set it to 0? Not really,
No.
right? Okay. But graphing a polynomial is boring. Like, we want to be able to graph something more complicated, right? Something much more complicated. So we want to be able to do something like, I don't know, go look at another example here. This one is not very complicated. This is a rational function, but I think we should look at it. So here we go. I want to do the same steps for this. So take a second, get me the derivative, all right? We're going to need it. And if you want, try and set it to 0. Be right back. I'm going to be taking a derivative here. Okay, there's the derivative. Notice that I took this derivative and I didn't just leave it as a raw derivative, right? I cleaned it up algebraically. And up to this point in this class, most derivatives I've asked you for have just been the raw derivative. I haven't asked you to do anything algebraically with them, but I warned you that you would at some point have to do the algebra. And so we're there. Okay, we're gonna have to set this thing equal to 0, right? Before I get too far ahead of myself again, keep forgetting to tell you all this at the beginning, let's talk about the domain of this. Is there anything you cannot plug in?
Negative, well, actually, you can actually plug in anything and it'd be fine because the squared would make it positive.
Yeah, so it looks like maybe you'd have a problem, but there's no way you can ever make the denominator 0. You can't, no matter what you plug in, because you're going to square it, it'll become positive, then add 1. Even if you plug in 0, you'll still add 1, it won't be 0. And if you try a negative number there, you square it, it's going to be positive. So there's no way to get a division by 0. So the domain of this is everything, which means any critical numbers I find are guaranteed to be critical numbers because they're in the domain. So I take my derivative quotient rule, right? I don't have to go through that, I hope. Quotient rule, there's my derivative. Now I need to go about the 2 tasks, right? Which is figure out where's the derivative 0. I'm trying to find the critical points now. Where's the derivative 0? Where's the derivative not exist? All right, set the derivative to 0. Now I told y'all something a while back about fractions and when you set a fraction equal to 0. What did I tell you? If you ever have a fraction equal to 0,
Multiply both sides by the denominator.
you can multiply both sides by the denominator, which would mean that really the only thing you have to worry about is the numerator, right? Because you can always clear this fraction out by multiplying both sides by the denominator. So the only issue we have here, I'm going to say it the way I say it normally. A fraction can only be 0 if the numerator is 0, right? A fraction can only be 0 if the numerator is 0. So all I'm going to do here is forget about the denominator and just set the numerator equal to 0. And then how you solve that's up to you. There's a couple of different methods. I'm going to just do it this way. I'm going to look at it as a difference of squares. And then set each of those to 0. And I get 2 solutions, 1 and -1, plus or minus 1. Questions on that? What about the derivative not existing? Is there ever an issue with this derivative? Is there something I can plug in that's going to cause it to go crazy?
Not that I know.
Yeah, same thing. We cannot make this denominator 0. What about if the numerator is 0? Big deal. 0 is okay. I mean, if you plug in 1, you get 0. Big deal. 0 is a number, right? We're looking for things that cause this thing to go crazy. So we're saying, can you get division by 0? Is there a square root of a negative number, right? If it's a trig function, is it, trig functions, some of them have domains like tangent, right? You can't plug certain things into tangent, can't plug certain things into secant or cosecant. So right now, this is a nice function, like relatively speaking, it's nice. So there's no issues. So there's nothing here. So we have 2 critical numbers. What do I do with them? So what next?
Put them on the number line.
Yeah, put them on number line. -1 and 1. So one of my first semesters doing Cal 1, I was showing this method, and this was at a university. And when I introduced myself first day of class, I introduced myself, my name's Robert, blah, blah, blah. I like to go by Robert, but you can call me Robert, you can call me Mr. D, whatever. It was weird. I was like, 24 years old or something like that. And it was weird because my students were very young. I was like, call me Robert, just don't call me Bob or Bobby, because I don't go by Bob or Bobby. So I had this one student, he was like 10 years older than me. And he was like, I don't know, he just didn't like me. And when we did this method, he called it the Bobby method, just to piss me off. But whatever, call it whatever you want. I don't mind if you call it the Bobby method. That's fine. Okay, here we go. What now? I'm trying to distract you so that you forget what you're supposed to do.
Now we pick test numbers inside of
Test
intervals.
ones, right? Anything you want, right? We've got 3 regions, so -2 looks good, 0 looks good, 2 looks good. Could you have picked -3? Sure.
Yeah, I don't know why
Could
not.
you have picked -pi?
Yeah, that'd have been awful.
Yeah, I wouldn't recommend it though. I mean, do you really want to plug -pi into something? Right? No, right? So pick numbers that make sense, that are clean. All right, where do these numbers go?
Plug them into our derivative.
Derivative, right? Derivative. So this is where students start to mess up this method with the closed interval method. Because when you do the closed interval method, 4.1, you find the critical numbers and then you plug those critical numbers into the original function. That's different. That's not what we're doing here. Here, we're finding the critical numbers, then we're picking test points, and the test points are going into the derivative. So it's very distinct procedures here. Here we go. These got to go into the derivative. Bobby method. I think I told you that story about that student that came into the tutoring lab and told me I needed to correct myself because, you remember that story?
Yeah, when you were in college or something.
Yeah, when I was a TA and who cares? It was the same guy though. It was the same guy. He just really, he wanted my head. I don't know why. Okay, so I look at my derivative. Here it is. And I'm going to take this derivative and I'm going to start plugging things into it, right? So check this out. I'm going to work a little smart here. I know that the entire denominator is positive, right? Because no matter what I plug in there, x squared plus 1 will be positive, and then I square it, it's still positive. So I don't even care about the bottom at all. Understand? Whatever the numerator turns out to be is what the whole thing turns out to be. So if I plug -2 into the top, what happens? Square
Get
it.
-3.
You get -3. So this will give us a negative number, which means that we are less than 0, right? So my derivative over here is less than 0, which means my original function here is going down, right? Looking good. All right, now we plug 0 into the derivative. If I plug 0 into this, I get a 1 on top and the bottom is positive. So this should give me a positive number, which means that it's greater than 0. So my derivative here is positive, which means my original function is going up. So I'll always have a student ask me, do we have to check all of them? Like if we find the first one, can we just assume that it's going to continue to switch each time? Right? That would be convenient if that were the case, right? It's not the case. If that were the case, I would have told you that. But you have to check each one because it is possible to go like down, down, up, up, or down, up, up, down. You know, it can vary. It depends on the function. So now we did the last one. Plug in 2, you should get a negative number. And so the derivative here is negative, which means the original function here is going down. Ready to answer some questions. Are there any questions from you at this point? So let me figure out where the function is going up. I think that's happening here, isn't it? That's between -1 and 1. And it's going down over here forever and over here forever. So that's between, or that's negative infinity to negative 1, union 1 to infinity. What's left? What do we need now? This is part of our answer, right? Here we go. That's where it's going up and down.
We need our local max and min.
Local max min. Do we have any?
Yeah, at the -1 and the 1.
Okay, so let's talk about local max, local min. Local max. There we're looking for up and down, right?
Yeah.
That would be in this place right here, up and down. And so it happens at 1.
That one should actually be an absolute maximum as well. Just from what I can tell about this graph.
Yeah, if you've looked at the graph, yeah, if you've looked at the graph, then you probably determine that. I'm going to take 1 though. The important thing is I'm taking that number 1, I'm plugging it into the original function now to actually figure out how high it went. So if you plug 1 in, go back to the original way up here. If you plug in 1 in, you get 1/2, I believe. And what happens if you plug in -1? You can get -1/2. Do y'all know what I'm doing? Just plug that number into the original. Y'all ready to see it? You ready to look at it? There's the graph. That's the graph of the function. And if I click on it here, the computer's going to actually find that. See it right here? That point 1, right? The x coordinates 1, the y coordinates 1/2. That is a local maximum. And we have a local minimum here. All right. One more thing I want to point out here. Between here and here, right? Between there and there, my graph is going up, increasing, right? Increasing. And if I look here, the graph is going down, and then also over here, the graph is going down. So that's what my little chart thing said, right? Between -1 and 1, here our function should be going up, here our function should be going down, here our function should be going up. That's what we had, right? No, hold on, down. That exactly matches what I'm seeing here, right? All right, now it's 2:10, and there's no way at all that I can get through all of these. So I want you to pick, let's pick one of those. What do y'all think? Which one of those do y'all want to see?
I want to see 6.
6?
Yeah. Cosines and sines have funny graphs. I want to see what that one looks like.
Okay. Any other? No one else cares?
I was thinking number 8.
Yeah, I was gonna say 8 as well.
It's the natural log. That's what the interval is. They're going to be from greater than 0.
Yeah, so look, let's do this. Hunter, I'm going to pick up, look at this one down here, Hunter. That's another one with sine and cosine in it. Why don't we grab this one because it has a log? Now I think about it, I like this one because we have a domain restriction here. We have some domain issues. I like that one. Let's do that. Sorry, this is a what do you call it? A democratic, what do you call it? Democracy, where people can have a say, but ultimately the dictator just says, shut up, I don't care. What is that called? What type of society is that?
Democratic monarchy?
Yeah, basically, right. A democratic dictatorship. So I asked him, what do you want? And I don't care, I'm gonna do what I want. Okay, so here we go. Let's do domain first. Okay, I'm not gonna forget this time. Let's talk about domain. All right, so we have a natural log in here. Everyone hopefully remembers that natural log functions, you can't plug 0 in, you can't plug negatives in, right? No zeros, no negative. which means that the domain of this is 0 to infinity. That means if we get any critical numbers that aren't in here, then they aren't critical numbers. We throw them out. All right, here we go. I need the derivative. So I'm going to use a product rule, yeah? 2x natural log x plus 1 over x times x squared. So, right, product rule, derivative of x squared, 2x times natural log x plus derivative of natural log x, 1 over x times the first function here, x squared. Yeah, yeah. That clean? Clear? Clean it up?
Could we clean that up to just be plus x on that?
Yeah, exactly. I'm gonna do plus x, just cancel out one of those x's. There's my derivative. Actually not that bad looking, except it has a natural log in it, so you're not happy about that, but otherwise pretty clean. Let's go ahead and take a look at the two things we need. We need the critical points, right? Sorry. Critical points. Let me do it on the side here. So the critical points, I'm going to take my derivative, set it equal to 0. I'm going to figure out when my derivative doesn't exist. All right, derivative equal to 0. Plus x equals 0. We need to solve this equation. GCF, they both terms have x, right? Pulling
Yeah,
x
we
out.
can just factor out next.
Okay, 2 natural log x plus 1 equals 0. So I pulled an x out of each term. And then once I do that, I can set each factor to 0. So x equals 0 is 1. And then I set this to 0. 2 natural log x plus 1 equals 0. X equals 0 is one potential critical number, potentially. And then this one here, I have to solve. So I'm going to subtract 1 on both sides. I'm going to divide by 2. And that got my natural log by itself. And then what I'm going to do is kill the log with e. So I'm going to come in here with e natural log x equals e to the negative 1/2. And that gives me x is equal to e to the negative 1/2. Which is just a number, right? You could look at that if you want as 1 over e to the half. And that could be looked at as in 1 over square root of e. But at the end of the day, it's just a number, right? That's just some number. Critical number. Questions? I'm throwing that one out. Why?
Because it's equal to 0, and this
You're
has a
right.
domain restriction.
That's a domain. I have a domain restriction, right? I cannot plug 0 in. I have to throw that one away. Okay, so I'm not even going to consider it. Now, I need to figure out where the derivative doesn't exist. Okay, this is a little bit tricky. Here's the derivative. Are there anything that's going to cause that derivative to go crazy?
If x is 0 or a negative.
Yeah, we have a natural log in there again, right? So we can't plug in anything that's 0 or negative, right? That would cause a problem. But my domain restriction already is keeping me away from that, isn't it? My domain restriction is saying, hey, you're not allowed to look 0 or negative. So I have no critical numbers from this either. Does that make sense? Even though I know that that x has to be greater than 0 to actually be a valid function, I don't have to worry about anything other than that because of the original domain of the function. So I have how many critical numbers then?
1.
Just 1. So I'm just going to put 1 number on the number line. Now, if I wanted to know what 1 over the square root of e is, I could get on my calculator and figure that out.
What's e roughly equal to?
2.718.
All right.
Yeah, so maybe
It's about 0.6.
the whole thing, 1
Yeah.
over this.
Yeah, I don't have a button for E, so I just used the 2.718, so
Okay,
it's not
about
exact.
0.6.
Yeah,
It would be worth it for you to figure that out as a decimal, because you got to pick a test point to the left and to the right, right? So look, to the left of this, y'all agree 1 over square root of E is a positive number, right? It's positive. So you cannot do this. You cannot try and be clever and pick 0. You can't do that. Why?
that's in the domain restriction.
We have a domain restriction. We can't plug 0 in, right? So you have to stay to the right of 0, right? So what I like to do, because of my domain restriction, I like to put 0 here. And then what I like to do is I put another dotted line here, and then I just kind of scratch all that out. I'm not allowed to look over there, right? There should be no graph over there at all. The function doesn't exist over there. So I'm not even going to look there. So that means my test point needs to come in here. I don't know. I'm just going to pick 0.1. I'll pick a decimal. And then over here, I'm going to be a little smarter. I'm going to pick 1. And these get plugged into the derivative. Into the derivative. Into what?
The derivative.
Derivative. Test points go into the derivative. All right, we go. Plug them in. Where's my derivative? Here it is. Grab it. May need a calculator here. Now, plugging in 1 will be easy. Okay, I'm going to plug 1 into this because I know what happens here. 2 times 1 is 1. I mean, so I thought I knew what happened. 2 times 1 is 2. The natural log of 1?
0.
0. Okay, so that kills all this. Plus 1. So that's going to be a positive number. Greater than 0. And if you plug in 0.1, do that on your own. Calculator, plug in 0.1. You should get a negative number here. So the derivative is negative here. The derivative is positive there, which means the original function is going down here and the original function is going up here. This means that my original function is increasing on the interval 1 over the square root of E to infinity. And my original function is decreasing where?
From 0 to 1 over the square root of E.
0 to 1 over square root of E. Remember, you can't go to negative infinity, right? You can't. It's only decreasing in here. That's where it's decreasing. And it's increasing over here. That's this part, right? All right, next thing. Do we have any local max and local min? Let's see. Local max, local min. Let's talk about it. How about local max? Do you see our graph? Does it go up and down?
There isn't a local max.
There's none, right? You don't ever see it go up and down. It goes down and up, but not up and down. So we have none. None. No local max. Okay. No local max. L max, local max. Okay, what about local min? Yeah, it goes down and up, right? It happens at
1 root E.
1 over root E. So I've got to plug that into my original function, the original function, which was, what was the original function?
X squared times the natural log of X.
X squared natural log X. So that means I'm going to take 1 over the square root of E, square it, and then natural log of 1 over the square root of E. Right? This is 1 over E. I square the top and bottom. Check out what I'm going to do on this one. Watch. I'm not going to use a calculator. I'm going to rewrite this as natural log of E to the negative 1/2. Right? Wasn't that what it was originally? E to the negative 1/2, and then I dropped it down and then took the square root. Right? Then I'm going to take this and I'm going to use property of logs. I'm going to pop this out front. Or if you want, you can just use the fact right now that natural log and E kill each other off, however you want to look at it. But the 1/2 would come out front. Negative 1/2 would come out front. And then we have natural log of E. What's natural log of E? 1. So this just becomes times -1/2. And if I multiply straight across, I get -1/2e. That'll be my local minimum. You could find that as a decimal, but that's the exact answer. Just not enough time, not enough time. Questions? We're gonna look at the graph. Any questions?
With one like that, you would want the fraction answer, not the decimal answer, right?
I mean, I wouldn't be mad if you gave me the decimal, you know?
Okay,
I wouldn't be like, I wouldn't count it wrong.
okay. But, all right,
There's the graph. See, the computer doesn't give you the exact answer, it gives you decimals, right? Local minimum, right? That's all we had, local min. The graph doesn't exist to the left of 0. There's your picture, right? Down then up, down then up.
from what I can tell, computers don't seem to like fractions a whole lot.
They love decimals.
Yeah,
And in Cal 2, you'll understand why they love decimals.
it's all, fractions seem to be something that humans do for ourselves, but they don't translate well to a lot of things, but they're necessary for a lot of stuff as well.
Yeah.
They're weird.
All right, so I'm trying to decide here how I want to go about this. There's so much more that we can do, but we're only halfway through the section in terms of the material. So I think what I'm going to do right now is I'm going to choose to say, all right, let's pause on doing more of these, and let's go talk about the second half of this section. Right now, what we've discovered is this thing called the first derivative test. It allows us to take a look at a function, figure out where it's going up and down, and from that, we are able to find the local maximums and local minimums, right? That's what we've got. How complicated the functions get, we still have to experience, because these problems get harder, right? The functions get crazy. The algebra gets nasty. But conceptually, the idea is easy, right? I mean, not easy, but you know what I'm saying. So now we move on to this new idea that a lot of you have probably never heard of. And it's something called concavity, all right? Concavity. So when I talk about a function is increasing and decreasing, I think everyone understands that in the sense that the function goes up or down, right? As you read from left to right, the function is either going up or down. Okay, increase, decrease, big deal. Concavity is a similar idea, but it has nothing to do with whether or not the function is going up or down. So I'm going to show you right now a function, okay? And I want you to pay attention to the regions that are going to be colored here. Okay, you see those colored regions? Look at the red region on the left right here. Look at this region right here. On part of this region, the function is increasing, right? You could say like on this side, the function is increasing. Then we get to the top and then it's decreasing, yes? So what's in red is not representing the up or down. It has nothing to do with up or down, right? It's something different that I'm highlighting here.
It's just the curve, isn't it?
It has something to do with the shape of that curve. And then look at the green part. You see the green here, right? This green is somehow a different shape than this red one. And then this red one is different than this green one. And then this green one is different than this red one. What the hell's going on here? It has to do with
whether
this
the
idea.
curves opens up or down.
Yeah, exactly. It has to do whether or not your curve looks like a smile or whether it looks like a frown. Okay, that's basically what it comes down to. If you look at the curve now, do you see in this red region, you could consider everything on this curve to be part of a sad face, right? Like, you know, I know this is very childish, but you know, sometimes that's the way life is. So this is like part of a sad frown right here. And then this green is like part of a smile, right? It's only like half the smile, but it's a smile, not a frown. And then over here, this is a little frown, right? And then this part over here is part of a smile, right? Do y'all see that? And these points right here, right? Those points right there are where we have this transition where we actually change from a frown to a smile, right? So it's like, I'm sad, I'm happy, I'm happy, I'm sad, I'm happy, right? That's basically what's going on here. That's what concavity is. Concavity is whether or not you got smile or frown. Now, there's a more precise definition, okay? Because if you look in a calculus book, it's not going to be like, oh, it's where it looks like a smile and a frown. That's not what it's going to say. But you know, visually, that's what it comes down to. What it really is this. It's kind of hard to see. I'll show you what concavity really is. Let me back this up. Look at right now. I'm on a frown, right? Do y'all see I'm on the frown? And do you agree that the tangent line is always above the graph? That tangent line is always above the graph. Above the graph, tangent line still above the graph. Tangent line still above the graph until you get to some point right around here, and then now your tangent line is below the graph. Do you know what I'm saying? Like this tangent line, the points on this line are below the points on the graph in this little region right here. And anytime that happens, you have what's called concave up. If I go to right here, it switches. Now the tangent line is above the graph until I get to here. And now the tangent line is below the graph and it stays below the graph. That's the more precise idea of concavity. It's the relationship between where the position of the tangent line is to the graph. But I want you to think smiles and frowns, because really that's all you need, smiles and frowns, all right? So for graphs, right? For graphs, there's a way we can determine where a graph is smiling and frowning. We can find out what it is, like where it happens. Just like we were able to tell when a graph went up and down, there's a way to tell where it's smiling and frowning, and it has to do with the second derivative. It's everything we just did, but with the second derivative instead of the first. So let me get to the second derivative. No. Yeah, well, here we go. Where are my notes? There it is. Oh, I went too far. Here we go. This is me giving you the more precise definition. If a function f lies above all its tangents, just ignore this, okay? Just ignore it. Concave up, concave down. Smile and frown. So if the second derivative of a function, second derivative is positive, greater than 0, then we are concave up. The function is concave up. If the second derivative is negative, then we're concave down. What's nice about that is when you think about a smile, right? Positive people like to smile, right? Positive second derivative smile, right? Negative second derivative frown. So what we need to do now is figure out where we have this smiling and frowning happening and where it changes. When you have a point on the curve where our concavity changes from either a smile to a frown or a frown to a smile, that point where they change is called an inflection point. Inflection point. So I'm going to point out the inflection points here on this graph. So right here on this graph, we would have 1, 2, 3, we would have 3 inflection points. It's where the concavity of the function changes. And it doesn't matter. It can go from frown to smile or smile to frown. Wherever it changes, you have an inflection. With me? Okay. So the good news is that we don't have to do a lot more than we've already done, but we do have work to do. So look at this last part that I didn't do. I canceled, I crossed out. I would like for us to now do this. Find the intervals of concavity in the inflection points. So let's revisit the first problem, all right? The first problem we did was this one, right? We were able to figure out where the function went up and down, and we found local max and local min, and we were all happy, weren't we? We're all happy. Now let's talk about the concavity of this function. So what I'm going to do is I'm going to copy this down. And if I'm going to talk about its concavity, I need to talk about its second derivative, not the first. So I need its derivative, which we did earlier. Here's its first derivative. 12x squared plus 6x minus 6. That was the first derivative, right? That's what we used to figure out up, down, all that. But now we're going to take a look at the second derivative. And the second derivative is going to be 24x plus 6. Now that's a really clean derivative, isn't it? That second derivative is very nice. It's linear, it's beautiful. And I'm going to run through the same exact procedure that I just did for the first derivative. I'm going to find the critical points of that set of the second derivative. So I'm going to figure out where's the second derivative 0, where's the second derivative not exist. For a second derivative equal to 0.
We just solved that, right?
Are you asking me, or are you just saying we do just solve that?
Like, yeah, we just subtract 6 and then
Yeah,
divide by
subtract 6,
24,
divide
yeah.
by 24. Yeah, that's it. So we're going to subtract 6, divide by 24, which is negative 1/4, right? 6 times 4, 24. Oh, by the way, is this allowed? Is negative 1/4 allowed? Remember what the domain of the original function was, right? It was everything. So this is going to be a critical number, but it's a critical number for the second derivative, not the first derivative, right? And then does it ever not exist? So this 24 plus 6, 24x plus 6, is that ever going to have an issue?
No.
No.
No issues, right? So we don't have any issues. So we only have one critical point of the second derivative. And so I'm going to do the same thing. I'm going to plot it on a number line. That's going to break my number line into 2 regions, and I'm going to pick test points. Something to the left, something to the right. -1, 0. I like 0. Where do these go? Where do these test points go? What am I trying to figure out? Concavity, right?
Yeah.
Concavity is determined by the second derivative. If the second derivative is positive, positive people smile. If the second derivative is negative, negative people frown, right? So everything I'm trying to figure out here has to do with the second derivative. So I'm going to plug these test points into the second derivative now, not the first, and not the original function. So I want the second derivative at -1, and I want the second derivative at 0. My second derivative is right there. You can see it. Yes. I like plugging 0 in. I get 6. That's positive. It's greater than 0. And if I plug in -1, I do get a negative number. It's less than 0. Understand? So now, the second derivative over here is negative, which tells me what about the original function? What does it tell me about the original function?
It's got a frowny face.
It's frowning, right? It's
Concave
going to
down?
be concave down, right?
Yeah.
Concave down. So the way I'm going to do that, you know how we just did, like I used up and down for increase and decrease, right? In the previous, what I'm going to do now is I'm just going to draw a little like concave down, like this. The second derivative being negative means the original function is concave down. The second derivative over here is positive, which means my original function here is, not second derivative. My original function here is concave up. We switch here, right? At -1/4, we switch. We go from concave down to concave up. We switch down to up. This is an inflection point. I have an inflection point at f of -1/4. I would have to plug -1/4 into the original function, and that would give me some answer. I'll let you do that on your own. Can you tell me where this function is concave up and concave down? Give me the intervals where it happens.
Concave down from -∞ to -1/4. And
It's concave down over here from -∞ to -1/4.
Concave
Concave
up
up,
from -1/4 to infinity.
-1/4 to infinity. Do y'all see this is exactly the same method as we were doing before, except what it's telling you is different, right? It's not telling you where the graph is going up and down. It's telling you where the graph is smiling and frowning, right? It's a different visual result. Let's look at this. I want to go back and look at the graph. Here was the graph. Where was it happening?
-1/4.
Yeah, -1/4. Oh, you know what? The graph isn't doing it here. Let me see. Hold on. Let's call this f of x equals that. Let me plot -1/4, comma f of -0.25. There,
Yeah, all right.
there's the point. Y'all see this to the left? There's my inflection point. To the left of this point, I'm frowning, right? To the right of this point, I'm smiling. The point at which they come together, the frown and the smile meet, is called the inflection point. All right. Yeah, so there's good news that this concavity is the same procedure. The bad news is that you need the second derivative. So think about these problems that as the functions get more complicated, your first derivative is going to be bad, and then you're going to need a second derivative. And you're going to have to do all the algebra on that. So it's going to get messy. All right, it's going to get messy. All right, so here's what I'd like for you to do to keep you kind of on task. What I'd like for you to do for homework is just focus on these problems right here. See what you can do. I'll send this out as a file later. See what you can do just on these first 10. I'm sorry, 2 through 10. All right. Follow the instructions to do parts A, B, and C. So we've already done some of this, right? For number 2, 4, and for 8, we've already done the first part, right? We did part A and part B. You need to take the second derivative and do this thing. See how it goes. You're going to run into issues. I know you will, but do your best. See how it works out for you. Okay.
Where are you going to send this out?
That same folder where I'm putting all the Zoom notes. Yeah. These are problems right out of the book, the textbook, the ebook. This is problem for this section 4.3. It's problem 2, 4, 6, 8, and 10. I picked the evens because the solutions aren't there. So I figured I would do them. All right, you're free to head out. You can go. I was just going to discuss real quick an inflection point and why the inflection point is important. If any of you ever take any business classes, you'll hear about this thing called the point of diminishing return. I don't know if you've ever heard that terminology before. Imagine you have a function that does this. Okay. And let's say this is time, and let's say this is your profit. So you have a company, and as time has gone on, this is your graph of your profit. And so what's good about this is that you look at this and you're like, well, hey, look, our profit keeps going up, right? As you move from left to right, as time has gone on, our profit keeps increasing, right? It's increasing. But something happened right here. This is where the left side was a smile, right? And the right side is now the frown. Now, do you all agree that in both the green and the red, we are increasing? The function is increasing, right? But something has changed. If you look at any point on this green, like look at how steep those tangent lines are. See how steep they are, right? They're steep. And so your profit was going up, but it was going up at a higher rate because they were steeper. Once you get past this point, you still have positive derivatives, but do you see how they're starting to flatten out? Right? They're starting to flatten. And what that means is that even though your profit is increasing, it's not increasing at the same rate. It's slowing down. The rate at which the profit is increasing is slowing down. Yeah. So that's an important point in statistics. When you model things statistically within a business, if you have inflection points, you want to know what happened there, right? It's like, who did we hire? Who did we hire right then? Because something happened. Our profit started to not diminish, but they started to, what's the name they use for that point? The point of diminishing return. That is the point at which the return, the profit starts to diminish. You're still profiting, but you're diminishing. The point of diminishing return. That's the inflection point. Okay, we got to go.
Isn't that like directly analogous to acceleration?
If this were time
Like-
and distance, then that would be.
Yeah, isn't acceleration also the second derivative?
Mhm.
Okay, just wanted to make sure I was remembering it correctly.
So this happens, this point, if we change this to distance, and we change this to, well, we can go time still. Right, then you could tell me here that your velocity was always positive, right? Because your derivative is always positive. The first derivative is velocity, the second derivative is acceleration. So what's happening right here? Your acceleration is what here? 0.
Yeah,
Your
holding
acceleration
a
is 0.
constant velocity at that moment.
Yeah, so your acceleration at that point is 0. To the left, your acceleration was positive, and then to the right, your acceleration was negative. So think of it like your gas pedal. Okay, so like what's happening here is that here you're stepping on the gas, right? And you keep stepping, you keep on increasing the accelerator, and then you stop. Okay, you stop. You still have your foot down on the pedal, but you stop moving it, and then you start releasing the gas pedal. So now you are decelerating. You have negative acceleration. All right, we can get into this more and more, but work on those homework problems, because like I told you, the challenge is going to be getting that second derivative, solving the equation, right? The conceptual part, I think, is straightforward. Take the derivative, set it to 0, test points, all that stuff. But it's the actual algebra that's going to get tricky. So, all right. We'll be back Thursday.
Could I ask for one favor?
Sure. Yeah.
The notes for last Tuesday.
Did I not send it? Really? For 11/9?
There's something there, but it's not the notes that we had for last Tuesday.